Friends, let me tell you about a mathematical constant that you see everywhere in mathematics. This constant number is 2.718. You will find it everywhere in mathematics, physics, and engineering. But the question is, where does it actually come from? Why is it so special? And why is it so common in exponential growth, Fourier transforms, complex analysis, and electrical engineering? Even though it is so common, most of the time in mathematics, we are not taught about it in depth. So let's try to find out today where it actually comes from and why it is useful for us. So basically, we'll start with what exponential functions are, why they are important, and how e comes from exponential functions. So before understanding the number e, we need to understand exponential functions. Simply put, exponential functions are those functions that grow very rapidly, and the concept of their growth is based on compounding. To understand this, first let me introduce you to linear functions, and we've been studying these types of functions since childhood, where two functions are mapped to each other linearly. For example, y equals 2x, 5 equals 5x, and so on. So we call these types of functions linear functions. Now, to understand exponential functions, we compare them with linear functions. So let's take four functions: y equals 2x, y equals 3x, y equals 2 to the power x, and y equals 3 to the power x. Out of these, 2 are linear functions and 2 are exponential functions. Now, to understand exponential functions, let's make a table and see how their values increase. Here, we take x from 1 to 5. So basically, we will plot the values of x in the function. So in the case of y equals 2x, basically we are multiplying the number by 2. So what result will you get? 2 and 2 times 1 is 2, 2 times 2 is 4, 3 times 2 is 6, similarly 8, and finally 10. So basically, this function is multiplying the number by 2. Now similarly, we will look at y equals 3x. In this case, we will basically multiply by 3, so what will you get here? 3 times 1 equals 3, 2 times 3 equals 6, 3 times 3 equals 9. Similarly, 3 times 4 equals 12, and finally 15. So now, if you look closely here, this function is growing faster compared to 2x. But the real magic will appear before us when we look at y equals 2 to the power x. Now observe how our function y, in the case of 2 to the power x and 3 to the power x, grows much faster compared to a linear function. And also notice that 2 to the power x. And how much difference is there in the growth between 3 to the power x and these? So 2 to the power x is basically a doubling function. Suppose we put 1 in place of x, so 2 to the power 1 equals 2, 2 to the power 2 equals 4, 2 to the power 3 equals 8, 2 to the power 4 equals 16, and finally 2 to the power 5 equals 32. So here you can see that as you increase the number, this function is growing just as rapidly, growing at a doubling rate. Now look at the case of 3 to the power x. So 3 to the power 1 equals 3, 3 to the power 2 equals 9, 3 to the power 3 equals 27, 3 to the power 4 equals 81, then 3 to the power 5 equals 243, and this also grew quite rapidly. So if you compare at what rate the function is changing, you'll see that exponential functions grow much faster compared to linear functions. And you can clearly see this in the table as well, that when you compare 2 to the power x and 3 to the power x, you'll notice that 3 to the power x grows even faster. Similarly, 4 to the power x will grow in an even crazier way. Basically, as you increase the base, you'll see that your exponential function grows much more rapidly, and it grows that way because its growth depends on the number that came before it. In other words, its growth depends on its previous number. So basically, this is a dependent function. But if you look at the case of a linear function, linear functions are independent functions because in them, you're only multiplying by a single number. Now to visualize this, let's plot them and see. So y equals 2x is a normal straight line. Similarly, y equals 3x is also a straight line. It's just that its slope is a bit higher compared to 2x, as you can see here. But now, if we try to draw e equals e to the power x, you'll see that this thing shoots up rapidly like a rocket. And similarly, y equals 3 to the power x shows an even more curvy behavior. And as the base increases, the behavior of this graph becomes sharper and sharper. So this is the real power of exponential functions. So by now, you must have gotten some idea of what exponential functions are. But now, where did this come from? So let's look at this as well. Basically, we will look at this in two ways: mathematically and intuitively. So now what you should do is plot y equals 2 to the power x and also plot 3 to the power x. So what will we do? We will take the derivative of these exponential functions, and when we take the derivative, we see something interesting. Meaning, we want to look at the rate of these functions. The rate at which the function is changing. So, d over dx of 2 to the power x equals 2 to the power x times ln2. Now, what is the value of ln2? It is approximately equal to 0.693. That means, obviously, this is less than 1, so the rate at which the function is growing, its derivative, is less than the function itself. In other words, the derivative of 2 to the power x is a bit slower than the function itself. As we've plotted it here, you can see that the actual function is growing faster than its derivative. You can clearly see this here because the value of ln2 is 0.693, which is less than 1, and the derivative of a to the power x is a to the power x times log a. So, when a value less than 1 is multiplied with our original function, its rate will be slower than the rate of the original function. This is quite an obvious thing. Now, if we do the same thing for 3 to the power x, its derivative will be 3 to the power x times ln3, and the value of ln3 is 1.098, which is greater than 1. So this means that the growth rate of 3 to the power x is a bit faster than the function itself, meaning the rate at which this function is growing is faster than the function itself. When you plot this, the derivative appears on the left-hand side of the function, which represents the faster growth. Now this is a bit strange. Why is this happening? Why is the derivative slower with 2, while with 3 to the power x, the derivative is faster than the function itself now? Now obviously, an intuitive question arises here. When one function is growing a bit slowly and another function is growing fast, the question is, where can you draw a line in between that separates the two, such that all the functions below this line have derivatives that move slowly, and all the functions above this line have derivatives that move fast. So, does this mean that there is a point in the exponential function that acts as an equilibrium? And the answer is yes, there is an equilibrium point here. This means, think of it like this. The derivative of 2 to the power x is less than the original function, and the derivative of 3 to the power x is greater than that function. In other words, there must be some number where the derivative of that function and the function itself are exactly the same, and that's where this property holds true. That number is our e, which is 2.718. So e is our equilibrium point here. Now look carefully here. If we take the derivative of e to the power x, the derivative of e to the power x is e to the power x itself, and this is a unique property. The derivative and the function of e to the power x are the same. That means this is a perfect equilibrium, and this property repeats itself again and again. No matter how many times you differentiate it, it means that e to the power x is such a function that which perfectly balances itself. This property makes it super powerful in mathematics, so here we have our equilibrium growth function. Basically, this is the only exponential function in which the rate of change is equal to the function itself. Any value that is lower than 2.718, its derivative will be lower than its function, and any value above that, its rate of change will be greater than the function, and this is quite a unique property. Now secondly, we can also look at its mathematical origin. Mathematically, it is defined as the limit as x tends to infinity of 1 plus 1 upon x raised to the power x. Think of it this way. Suppose you take a value. You raise 1 to an exponential, but at the same time, you add a small increment to it. That is 1 plus 1 upon x. So, look at this table here. We keep putting different values of x. When you put x equal to 1, then its value is 2. When you put x equal to 1, its value becomes 2.25. And in the same way, as you keep increasing the number, you see that this value is approaching e. When you put 10, it becomes 2.59. When you put 100, it becomes 2.704. When you put 1000, it becomes 2.716. And when you put 10,000, it becomes 2.718. So as x increases, this value converges towards 2.718. And this is the origin of e. So again, the number e is a pretty crazy number, and basically it's just a value where you see a particular kind of behavior, and this behavior of e makes our lives much easier, because if you take e to the power x, Whether you take its derivative, its integral, or even if you take its derivative infinitely many times, the rate of its derivative always remains equal to the function itself, and this makes our lives a lot simpler, especially when you're doing mathematics. And it also has significant importance in physics. If you define e as the limit as x tends to infinity of 1 plus 1 upon x to the power x, then if you multiply it by an imaginary number, that is e to the power iota x. Here we replace x with theta, so we get e to the power iota theta. So what did we basically do? We multiplied e to the power x by an imaginary number. So you see that when you multiply by an imaginary number, the function that was previously growing exponentially after multiplying by an imaginary number actually starts to rotate and begins to describe a circle. Well, we describe this using Euler's formula. We also call this Euler's equation, which states that e to the power of iota theta equals cos theta plus iota sin theta. But why does this actually happen? Why is it that when you multiply by an imaginary number, a function that was previously growing suddenly starts to rotate? What exactly did the imaginary number do? Why did it turn the function into an oscillatory and rotational one? What is so special about Euler's equation after all? Well, do let us know your answer to this in the comments section. For now, we'll talk about this rotating function in a different video. So guys, that's all for today's video. I hope you really enjoyed this video. If that's the case, then we sincerely encourage you to show your support by liking this video, sharing it widely with all your friends and family who might find it interesting or helpful, and if you haven't already taken the important step of subscribing to our channel yet, please make sure to hit that subscribe button and turn on notifications so you absolutely do not miss out on any of our valuable future videos, exciting new updates, or exclusive content that we will be releasing regularly.